Hello, everyone. My name is Rajesh Jha. I'm the founder and CEO at SimInsights.
Yeah. Hello, everyone. My name is Eric Navarro, and I'm a software engineer here at Insights.
We are going to talk about how the manufacturing industry can embrace XR, extended reality, and AI at scale to create digital twins for assembly operations. The title of our talk is No Code Authoring of XR Digital Twins for Manufacturing. XR digital twins are a special class of digital twins intended for real-time use on XR devices to guide human decisions and actions. I would like to begin by saying thank you to the people at NVIDIA Inception Program and in other groups at NVIDIA for supporting our work in very meaningful ways. First, we'll describe in detail the use case that we are addressing as we take our first step toward building a software tool for authoring XR digital twins with multimodal AI assistants. You can see our product concept in this picture, and I'll explain it more in the next slide. Next, we'll describe the approach that we are taking for leveraging XR and AI for quality monitoring. We'll then present detailed results on training and evaluation of the deep neural network models. We'll also cover deployment to HoloLens and Jetson Nano, followed by a discussion of the streamlined end-to-end workflow enabled by HyperMock, our software product. Finally, we'll present our conclusions and answer any questions. Our use case comes from Semicron USA, a division of the Germany-based power semiconductor manufacturer. We're focusing on the problem of artificial intelligence-based defect detection and monitoring in manufacturing assembly. Assembly here refers to manual assembly, where the workers follow a sequence of steps to complete a product. Workers in this domain rely heavily on written or displayed instructions, and mistakes are not uncommon, especially when the work is monotonous and repetitive. Although quality control measures usually allow one to identify errors, their correction costs extra time, and depending on the product complexity, delays can happen in shipments considerably. In a worst-case scenario, a faulty product ships to a customer, which entails warranty claims and more. To give you a sense of how big this problem is, just in the US, companies could have saved more than $25 billion in 2018 in warranty claims if all the products had worked as expected. We really believe that XR and AI-based solutions can mitigate some of this loss. But to have impact at scale, we must lower the barrier to use XR and AI technologies. And one of the things we have to do is create authoring applications that enable non-technical users to create XR digital twins and use them for training, guidance, and monitoring. Here's a picture showing our solution concept, where a manufacturing worker is being trained and guided by instructions, 3D visualizations, and voice, while also being monitored using computer vision. The assistant, the multimodal AI assistant, knows the task to be done, all the steps, but it can also see and hear what the worker sees and hears, and it can even have a model of the worker's knowledge and skills. So by combining all of these, it can provide contextual and personalized guidance to reduce the worker's cognitive load and increase the worker's learning, transfer, retention, and productivity. That is the promise of this technology, and that is our long-term goal. When such a solution is deployed on the assembly line, the digital twins can display instructions to the workers, overlay 3D models onto real-world objects, and catch quality issues. All of the work that we present today was done using Isaac Sim for Unity and Isaac SDK. Due to confidentiality, customer images could not be used in our presentation. So we created a testbed that is essentially equivalent in terms of fundamental technical challenges. And we present our results based on the testbed. But the findings apply to the general class of assembly problems. Here on the left, you can see a public picture showing the type of electrical and mechanical assembly tasks involved. And on the right, you can see our test bed, which contains a variety of objects with different geometry and appearance properties, including a wire. The general QA problem or quality assurance problem is simply to detect and prevent defects, ideally in real time. It is the real-time aspect that provides the strongest motivation for using extended reality or XR for quality assurance. Because when you have a worker wearing an XR device, the multimodal assistant can provide just-in-time quality feedback, which enables the worker to catch and correct defects early. Clearly, early detection of defects is much better than late detection. Another very important benefit is that XR allows quality assurance to be combined with employee training and onboarding. Training is, as we all know, is not a discrete binary process. It is rather a continuous process that over time transforms a novice into an expert. And if a software solution can combine training and quality assurance, then that software can help all the employees ranging from novices to experts throughout their career, and thus it can have a big impact. Now let's quickly review the history and present state of quality assurance, XR, and CV. So today, several task guidance XR apps actually exist. However, none of them include quality assurance. Also, computer vision for quality monitoring has a long history, but the use of deep neural networks is new. Now, what is truly innovative is the combination of task guidance with computer vision-based quality monitoring, and that's where we are focused. In our solution, we apply both traditional computer vision techniques and neural network-based approaches for different subtasks. We employ neural network-based object detection and pose estimation to verify if the correct items are in the scene or if incorrect items are present, all the correct items are in the correct orientation, and so on. And we apply traditional computer vision for detecting wires and other tasks. Here you can see an example. The picture on the left shows correct assembly based on all the right objects being present and their poses being correct. And the picture on the right is an example of incorrect assembly where some of the objects are in the wrong pose. And now I'll turn it over to Eric to discuss in detail the dataset creation, training, inference, and evaluation for deep neural network models.
Thank you, Raj. We'll start first with data collection and its effect on training neural net models. There are two dataset types in our approach: real-world datasets, which is video and images captured in the real world, and synthetic datasets, which is video and images generated from a virtual environment or simulation. The ideal process would use synthetic data to reduce the capture and labeling efforts associated with real-world data. In the next slide, we'll see how the real-world dataset fits into our neural net training pipeline. The real-world training pipeline begins with the capture of raw videos and images for the target use case scenario using fixed cameras, mobile cameras, or other devices and sensors. Once the data has been captured and stored, we begin the pre-processing phase. This includes actions such as resizing, grouping, and filtering videos and images. With our aggregated data, we proceed to the annotation step, where we label objects of interest that the model will be trained to detect. After annotating the data, we do additional post-processing, such as brightness randomization, on the annotated dataset. The next step in the pipeline is to begin the model training process, which we do so using NVIDIA's Transfer Learning Toolkit. Once the model is trained, the final step is to export the model for deployment and use. For our testbed sample, we manually captured 720p videos of the testbed from a mobile device. we extracted the video to a set of frames and resized the frames to 640 by 368 to reduce training time. We then annotated our data and performed brightness randomization to improve model performance in more varied lighting conditions. For a training pipeline, we chose to utilize a pre-trained DetectNet v2 model, which Nvidia provides through the Transfer Learning Toolkit. Each DetectNet model was trained using an RTX 2080 Super and deployed using Nvidia's Triton Inference server, which allows for quick and easy deployment of models. Before diving into the training results, it's important to cover some tips on how to capture high-quality real-world data so your models can learn and perform at their best. When capturing real-world data, you'll want to keep certain guidelines in mind. Keeping these guidelines in mind will help reduce training time and improve the accuracy and performance of your models. Keep the object of interest in focus at all times and avoid quick movements and blurriness. Include as many angles as possible and vary the distance and zoom of the camera. Make sure the resolution at which you're capturing your data matches what you will input into your object detection models. For example, our object detection model, the DetectNet v2, would expect input in 640 by 368. So it was in our best interest to capture data in a resolution of the same aspect ratio, or keep it as close as possible to minimize image resizing requirements. Also keep in mind the lighting when capturing your data, and try to avoid any extreme or unusual lighting conditions. You want to ensure the your training data matches the target use case as much as possible. Standard object detection training guidelines, such as having a good positive to negative training sample ratio, still apply as well. Following these guidelines will make it easier to train an accurate and performant model. Now let's jump into the training results. For the real-world dataset approach, we went through 5 iterations. In each iteration, we experimented with different dataset configurations and processing steps. In iteration 1, we focused on detecting the switch item with a dataset size of roughly 1,200 images. The average precision we saw for detecting the switch on the training dataset was around 97%. In our testing datasets, we saw the object was not being detected in a number of frames. We determined that the model was improperly trained because the resolution size of our training images did not match what the model was expecting. The model would resize the images, but the annotations were not being modified as well, meaning the model was improperly trained. In iteration 2, we added image resizing as a pre-processing step and brightness randomization as a data augmentation step. In our iteration 2 tests, our training accuracy remained high and the testing accuracy performed well. In iteration 3, we expanded the model to include the other objects in the testbed. We found the other objects also had high accuracy, except for the cylinder, which had poor accuracy. After reviewing our data, we discovered the brightness randomization values for reflective surfaces generated unusual or extreme lighting conditions, which would cause the model to mislearn the target object. In iteration 4, we decided to disable the brightness randomization, which in turn reduced the accuracy of all objects across the board. In iteration 5, we re-enabled the brightness randomization, but with tweaked brightness values. The tweaked values helped improve detection of the reflective cylinder, but did not impede detection of the other objects. At iteration 5, the model became usable for quality monitoring. The models were detecting the target objects at a suitable accuracy, and the predicted bounding boxes were good fits. At each iteration, we would also calculate the precision recall curve for each object, which would let us identify good probability thresholds for our object detection models. Here we have 2 sample PR curves for the box and the cylinder. A well-chosen probability threshold can reduce false detections while maintaining high recall or accuracy. In the next slide, we'll preview some sample detections from the trained neural net models. Here we have a few sample frames we used to test the object detection models. Each object was assigned its own bounding box color, with the white bounding boxes serving as a visual of the ground truth annotation. The object detection models performed fairly well given their limited dataset sizes. We were able to achieve good general performance by auto-generating varied lighting conditions in our post-processing step. Annotation effort, which was time spent annotating the ground truth data, was heavily reduced by using short video-based captures and running those captures through a custom Lucas-Canade filter. The Lucas-Canade filter made it easier for the human participant to annotate data by tracking objects using a computer vision-based approach. A human would only need to interject to correct tracking errors and reinitialize the annotation process. Overall, we found the real-world based approach to perform well, albeit with some detection issues for reflective objects and surfaces. However, the real-world based approach is not as scalable as we would like. Data collection and annotation takes time and effort, which may not be feasible for users who are under tight deadlines. Additionally, new scenarios or situations, such as a new product to be built out of new parts, require additional data sets to be captured. Object detection models may not be trained in a suitable time frame for use in production. To address these concerns, we look to synthetic data. Synthetic data has some general advantages over real-world data. Synthetic data capture is more generalizable. Simulation gives us full control of the scene, and thus we can use randomization techniques to quickly generate an infinite number of scenarios. A new scenario, such as the previously mentioned new product to be built, can be treated as just another simulation. The annotation effort, compared to real-world data, is also further reduced. There is no need for human participation since the annotation and labeling is performed automatically. Labeling error is reduced and can be scaled as needed. Synthetic datasets still have some issues that need to be addressed before they can replace real-world datasets. In order for the object detection models to perform well, the simulation should match the real-world counterpart as much as possible. This means the 3D models must be of high fidelity, with appropriate high-quality textures and reflections. The scene must also be laid out as well to match the real world, which will require human effort. Finally, there's a computational cost to generating these randomized scenarios. If you're generating the scenarios on the same device as you're training your models, this cost is reduced. The synthetic training pipeline begins with the import of CAD models into Nvidia's Isaac Sim for Unity. Once all models have been imported and the scene is laid out, we begin the synthetic data capture, which saves annotated synthetic data for use in training. From then on, the training pipeline is the same as the real-world pipeline. We once again use Nvidia's Transfer Learning Toolkit using the same DetectNet v2 model type. Deployment to Nvidia's Triton's Inference server also stays the same. Because our synthetic dataset sizes were larger than the real-world datasets, we decided to use a Nvidia Quadro P6000 over the RTX 2080 Super to reduce total training time. For our testbed sample, we used 3D models of our target objects and imported them into Unity. We set up a scene for data generation using new Unity standard tools and used Nvidia's Isaac Sim to generate the randomized synthetic data. Before discussing the results, let's review some tips on generating high-quality synthetic data. As mentioned before, for synthetic data generation, we use Nvidia's Isaac Sim for Unity and the Isaac SDK. Our first approach was to use simple domain randomization scripts, which would randomize object textures, lighting, positions, and rotations. As an example, you can imagine a virtual scene where we have the panel from our testbed and we randomly sample a new checkerboard pattern that we apply. We also then randomly rotate it and position it somewhere in view of a virtual camera. The idea is, with simple domain randomization, we can train a model to learn what the objects look like based on their 3D geometry. However, we found that the simple domain randomization would not perform as well as we would hope for our target use case. Therefore, we wrote our own randomization scripts to perform what we call structured domain randomization. Structured domain randomization still randomizes the scenarios, but it does so in a way that closely matches the real world. This means that we removed the texture randomization and opted for more subtle color variants, which could help account for differences in device camera qualities and minute lighting changes. We kept the location randomization, but we restricted it to regions and improved the object collision detection, so objects would not clip into each other unnaturally. We kept the lighting randomization, but made reflection randomization more subtle. We found the best improvements for our models when following these guidelines and randomization techniques. Let's move forward to the training results. As with the real-world training approach, we went through 5 iterations, tweaking the data generation strategies each time. In our first iteration, we used simple domain randomization, which, if you recall, would randomize textures, lighting, positions, and rotations. We found the results to not be satisfactory, with the model performing very well on synthetic data, but performing very poorly with too many false positives or detections in our real-world tests. Because the models perform so well on the synthetic data but not the real-world data, that's when we decided to shift towards structured domain randomization to make the synthetic data match the real world more closely. In our second iteration, we found the model did improve, with fewer false detections and better tracking across frames. Following this success, we tested additional changes, such as adding more negative samples, which are samples where the object is not in view, and mixing the simple and structured datasets. These changes further improved the object tracking across frames and made the bounding box tighter. In our fifth iteration, we further improved the randomization scripts and also added distractor objects, which help teach the model to ignore objects that look similar to but are not the target objects. As with the real-world training pipeline, we also generated PR curves at every iteration to help us choose a good probability threshold. Now that we've gone over both approaches, let's review what we've seen so far and compare them. In terms of setup and initial testing, small real-world datasets are easier to collect and use for training. As data requirements grow, synthetic data would be a more suitable approach. Once the initial setup for synthetic data is complete, additional data generation becomes much easier to do. Of course, there's no rule from stopping us from mixing the datasets, which is an entirely viable strategy. For example, you could collect real-world data to refine and improve the accuracy of models trained largely on synthetic data. You can also use synthetic data to cover edge cases or bridge gaps where there is not enough real-world data. A key takeaway here is that your object detection models will only be as good as the data you feed into it. Keep the guidelines we've covered in mind to ensure you have high-quality data which can be used to train high-quality models. With object detection covered, let's shift our focus to pose estimation, another critical component of the quality monitoring use case. As a note before we begin discussing pose estimation, our approach uses Nvidia's Isaac Sim and Isaac SDK, which only currently supports training pose estimation models using synthetic data. Therefore, we will not discuss training pose estimation models using real-world data. The pose estimation training pipeline begins with the import of 3D CAD models into Unity's Isaac Sim and the scene setup. The scene setup consists of placing the target object in the 3D environment and attaching randomization scripts to the target object and the virtual camera. This lets the pose estimation model see the object from many different angles as it's being trained. We then begin the data generation. At the same time, we launch a Nvidia Isaac gem named 3D Object Pose Estimation with Pose CNN Decoder, which takes in the synthetic data and starts training a pose estimation model with the data. The training can happen in real time as the synthetic data's images are being generated, as we did, or the training can happen on a set of synthetic images that were generated beforehand. Once the model has been thoroughly trained, it can be deployed. For our testbed, we trained a pose estimation model to estimate the pose of diplo blocks. For pose estimation, we went through 3 iterations. In the first iteration, we trained the model for roughly 1 day and with camera randomization only. In this iteration, the model output was unusable. To improve the accuracy, in our second iteration, we trained the model for much longer, roughly 6 days, and changed the training parameters to improve performance. Those training parameters include camera randomization, position randomization, and rotational randomization. With these changes, the rotation predictions improved, but the positional predictions were still incorrect. In our third iteration, we trained the model for 10 days and introduced additional randomization in our synthetic dataset. With these changes, the rotation predictions stayed roughly the same, but the positional estimations improved immensely. To the top right, you can see a sample of the synthetic data and the estimated pose of the object on that data. Below that is a sample of a real-world inference with the estimated pose of the object. The model is beginning to learn, but the accuracy is not at a point where it would be usable for a quality monitoring use case. The pose estimation module is still in progress, and we are exploring different techniques beyond the current randomization that could help improve the model accuracy. There is still a high computational cost to train pose estimation models, with the average training time for our models to be roughly 10 days, although this can be mitigated with stronger hardware and better software setups to minimize interruptions and errors. The model accuracy is still not at a point where it can be reliably used for quality monitoring, and the deployment process for pose estimation models is not fully fleshed out yet in our pipeline. Once these issues are addressed, pose estimation can be paired with object detection to provide full quality monitoring. To deploy the models for use in quality monitoring, there are some options available through Nvidia's offerings. As mentioned before, we use Nvidia's Trident Inference server, which allows local deployment of neural network models. The left side here, you can see a video snippet from our HoloLens experience, where users can take a picture of their assembly, send the picture to the local Trident Inference server, and get back object detection results. In the example, we take a picture of the diplo blocks and get back object detection inference results. Because both blocks were detected, the verification passes. On the right side, you can see a video snippet of inference running on the Jetson Nano in real time. The camera view is from our testbed. The Jetson is running an object detection model on device through Nvidia's DeepStream SDK. As a further example of how these models can all work together, here we have an example of object detection and a wire detection module working in tandem on the HoloLens 2. As you can see here, wire gets selected, and in the response, wire has been highlighted. So we've gone over our training processes for object detection and pose estimation, the differences between real-world and synthetic datasets, how to capture good datasets, and how the models are deployed. I'll now be handing it back over to Raj.
Thank you, Eric. Once we established the feasibility of using XR and computer vision for quality, we focused on streamlining the AI workflow for efficiency. When we gathered the user stories from manufacturing industry, what we learned was that this group was quite familiar with 3D, CAD, and other tools, but often lacked programming skills or training in machine learning and AI. So we found many opportunities to simplify and automate the typical AI workflows for our target audience and prioritize 3 to focus on. First, use of synthetic data to reduce the amount of real-world annotated data needed. 2, increase the efficiency of annotating real-world data by using tracking algorithms. And 3, try to combine AI training workflows with human training workflows by reusing 3D immersive training simulations built to train people for synthetic data generation to train AI. To rapidly iterate on these requirements, we decided to first develop a standalone prototype and test it out. Here's a video showing that prototype in action. So for training object detection models, we can upload real-world or synthetic data. To upload synthetic data, we can input number of objects, number of training images, and upload the images. For real-world data, we can upload videos captured with your smartphone, for example. And then we can label the images by drawing bounding boxes, as you can see here, and entering the string labels. We use tracking so that the users don't have to label every single frame. After the labeling is complete, we can launch training, and we have simplified this interface so our users have to input just the minimum number of parameters. And then the training begins, and we have a screen to monitor the progress of the training. And for testing, users can upload a different testing video, select one of the AI models to test with, and even manipulate the images if needed, like for example, rotate it. And here you can see how the system shows the performance of the network by drawing these bounding boxes. Another functionality we added was to be able to define relationships between the detected objects. For example, one object is above the other object, and the system can also check if these relationships are satisfied or not, and help with the quality monitoring. So you can see here a simple interface for specifying the objects and relations. You can have as many relations as you like. So here you can see the objects have been detected, including the wire, and the relationship is verified that the vent is indeed above the box. After validating the prototype, we began work on integrating it into Hypermock. Hypermock is a no-code application that enables users to author immersive simulations of facilities, machines, assemblies, and parts by reusing existing 3D CAD models. These immersive training scenarios run on PCs, web browsers, and XR platforms. Hypermock also enables non-programmer users to create branching nonlinear scenarios, for example, for training workers on procedural tasks, such as assembly, maintenance, and repair. What's really exciting is that these simulations can be reused to generate synthetic data sets to train deep neural network models, and thus reduce the need for real-world data. Once the neural nets have been trained, their performance can be visualized inside Hypermock in an interactive manner, as shown here in this mockup, which we are currently implementing. So these are pose bounding boxes showing the detection of different objects in the scene in our test bed. Finally, here is the overall workflow for XR digital twin authoring using Hypermock. First, existing 3D models are ingested. Here we are showing models coming from SolidWorks, but we can support other CAD software as well. After they have been imported, they get converted into interactive virtual objects and placed in an online repository. From there, the user can author immersive simulations by dragging and dropping the virtual objects and defining nonlinear branching scenarios inside Hypermock desktop application. Then the simulation can be used to train people in VR or AR. For example, here we're showing a screenshot from Oculus. And the simulation can also be used to train deep neural network models using synthetic data. Then the simulations along with the deep neural nets can be used on HoloLens for training, guidance, and quality monitoring. And when the simulations are used by the trainees, for example, we can collect additional data sets, which can be analyzed to derive insights about workers' proficiency, as well as to build user models, which can help personalize the instructions to the users. In summary, we thank NVIDIA for their support and for offering powerful SDKs and GPUs to help us accomplish the tasks in this project. We were successful with the object detection, and we are still working on improving the pose estimation model accuracy. We demonstrated the feasibility of combining computer vision techniques with XR to enable quality monitoring in manufacturing assembly. We also believe that the combination of quality monitoring with training is very promising for manufacturing. Our software solution is local and offline, so there is no need for cloud connectivity, which is really appealing to many manufacturers because it offers the benefits of low latency, privacy, and security, as well as lower cost. And with the addition of quality monitoring, Hypermock now offers a complete software solution for manufacturing companies to train, guide, and monitor their employees. And it's interesting to view Hypermock as a unified application for training both humans and AI models. Thank you for attending our talk, and we are happy to answer any questions.